All right, so this painting of an alchemist's laboratory was made around 1570. For centuries, these early scientists, known as alchemists, tried to use chemical reactions to make gold. Um, the alchemists failed in their attempts to turn lead into gold. So when we think about modern day chemistry, it was just a bunch of people way back in the day, literally almost 500 years ago, that were like, hey, gold is worth a lot of money. I bet you there's a way that you could take another metal and make it into gold. So how do artificial transmutations occur? Well, a transmutation is a conversion of atoms from one element to another. So we've been talking about decay, right? So when we talk about matter, we talk about alpha and beta particles, neutrons that are released from the sun that bombard matter here on Earth, and they insert themselves into different elements. And then those elements become slightly unstable, and over time, those elements, because they like to be in a state of equilibrium, will eject those particles. So scientists can perform artificial transmutations by bombarding atomic nuclei with high-energy particles such as protons, neutrons, or alpha particles. Okay? So transmutation involves a nuclear change, not a chemical change. We are changing the elements. So what that means is, if I have a chemical reaction between hydrogen, carbon, and oxygen, whatever happens, I still have hydrogen, carbon, and oxygen. A transmutation is where we change oxygen into nitrogen, or nitrogen into carbon, or carbon into nitrogen. There is a new element. So nuclear decay is an example of a transmutation that occurs naturally. That's the emission of extra particles that don't belong. But transmutations can also be artificial. We can force that. Now we can with the technology that we have. So in 1919, Rutherford performed the first artificial transmutation by exposing nitrogen gas to alpha particles. Some of the alpha particles were absorbed by the nucleus or nuclei of the nitrogen, and each newly formed nuclei then ejected a proton, leaving behind an isotope of oxygen. So they had nitrogen, they bombarded it with these alpha particles, and then changed it into oxygen and a proton. So this is a proton. Remember that hydrogen has one proton and one electron. So this is one way that we could label a proton. Okay. So how are transuranium elements produced? Well, elements are atomic numbers greater than 92, which is uranium, are called transuranium elements. And if you look on the periodic table, you could see them. Scientists can synthesize transuranium element by artificial transmutation of a lighter element. In other words, they take a lighter element that doesn't have as many neutrons in it or protons, and they bombard it with a neutron or proton in a way that they're forcing it to become another atom. So a transuranium element is going to be radioactive, right? We're changing the makeup of it, and they're not generally found in nature. Neptunium is or was the first transuranium element synthesized. In 1940, scientists at the University of California, Berkeley, bombarded uranium-238 with neutrons, producing uranium-239. The uranium-239 underwent beta decay to form neptunium. So when you watch the news and they talk about nuclear programs and uranium enrichment, what they're doing is they're creating these unstable forms of uranium, so that way if there's a nuclear reaction, for example, a nuclear bomb or just a regular nuclear reactor, because they're slightly unstable, that increases the nuclear reaction, which is good for nuclear energy. It's good for nuclear bombs too, but nuclear bombs are bad, obviously. So most transuranium elements have only been produced for research, and some were synthesized for industrial use. So americanium, and I'm pretty sure that I'm saying that sort of right. 241 is a transuranium element used in smoke detectors. The decay of plutonium 238 is used to generate electrical energy in some space probes. So they have little miniature nuclear reactors. They put this unstable element in there. The university that I went to school had plutonium. The plutonium was unstable, and we used it to charge particles for our lab experiments, which was really kind of cool. In 1977, NASA launched Voyager 1 and Voyager 2. They're still out in space to explore the outer solar system. They are powered by an alpha decay of the plutonium-238. So some transmutations require particles that are moving at extremely high speeds. Particle accelerators cause charged particles to move very close to the speed of light, moving these particles very fast and allowing them to collide with atoms produces these enriched elements, and so, or transmutated elements, I should say. Scientists have produced more than 3,000 different isotopes. So basically what they do is they speed up a proton or a neutron or an alpha particle really fast, almost to the speed of light, and bombard an element with it, and they just see what happens. Okay. Scientists also conduct collision experiments in order to study nuclear structure. So there's a couple of these particle colliders. There's a lot of particle colliders around here. Western University has a particle collider. It's a very small one. The Fermi Lab, which is in Chicago, has one. The Argonne National Laboratory near Chicago also has one. And they just conduct a lot of experiments. There's a big, huge, massive one that you probably saw on the internet called CERN that's over in Europe. That is the most state-of-the-art, large, fast particle accelerator on Earth right now. They do a lot of experimental work there. But basically, they just speed up these particles and collide them to see what happens. More than 200 different subatomic particles have been detected through these types of experiments. A quark is a subatomic particle theorized to be the basic units of matter. So remember a couple of sections ago, Mr. Adams said there are smaller things that make up the parts of the atom. According to the current model, an atom, the protons and neutrons are made up of quarks. So those are smaller particles that make up neutrons and protons. This particle detector records subatomic particles produced in the Tavotron, the most powerful accelerator in the world. The Tavotron is located in Fermi Lab. Now this is an old picture. Since then they have built a better particle accelerator in Europe in CERN. I've been to the Fermi Lab. It is impressive. It's a circle, and I think the radius is 2 miles. It's underground. Remember how Mr. Adams said sometimes you got to go underground to filter out the bombardment for particles that are emitted from the sun. But that's how big it is. It's pretty cool. And so they have a series of magnets that fire in sequence that force these particles to accelerate. They just go around in a circle and speed up and speed up and speed up and speed up and speed up. And then they, at the right moment, they slide something in front of it, smashes into it, and then they record everything. So which of the following is the type of atom transmutation? A, alpha decay. Remember, the alpha particles can collide into something. It changes the element. Remember, if you guys don't remember what an alpha particle is is 2 neutrons and 2 protons, right? So if you inject that into an element, because the element wants to remain in a state of equilibrium, it will eventually decay and kick those extra parts out. To study the structure of the atomic nucleus, scientists use particle accelerators to cause collisions of particles moving near the speed of light. Scientists use transuranium elements by the artificial transmutation of lighter elements. True. They take lighter things and bombard them with particles and make new stuff. And that's it. Any questions? No? Okay. So your assignment is posted.